Okay, here we go. Give me 1 second. Let me do a display capture on this.
Are you there?
Am I?
Can you not hear me? Can they not hear me?
Live. Okay, there we go.
Yes. Are you listening to me via stream?
Not anymore. I turned my...
Okay. Hold on, I'm getting this all set up too. And all right, so
Aren't you supposed to wear green now instead of purple?
Yeah, I know. It's bad.
give me 1 second, guys. Let me get this kind of configured so you guys don't see that. Here we go. And here we go. Okay. Sorry, thank you guys for being patient. Well, actually, we can make that like this. Sorry, I'm trying to get this all set up for OBS, and it's kind of, it'll be like another second. And you can actually start introducing yourself, Dr. Farr, if you would like.
You're really quiet for me.
I'm really quiet. Let's see. How about that? Is that better for you?
Yeah, it's a little better.
Okay. Here we go. There's Dr. Ben Farr, guys.
Hello?
You only have about, let's see, I don't know, 112 people right now watching. So that might not be accurate. That number changes all the time. So anyways, you can talk about yourself and what you do, why we're talking about gravitational waves, what you do with that, and
especially after 30 years of silence from you guys.
Well, it wasn't quite silent. There's a lot of noise, but yeah. So I work on a project called LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory, and specifically, what I do is I analyze the data coming out of the instruments, and my ultimate goal is to do astronomy with this kind of new window to the universe that we finally opened up. So LIGO picks up these vibrations in space-time called gravitational waves, which are literally ripples in the fabric of space-time that kind of stretch and squeeze space and time. And they're created by lots of different things, but the most interesting stuff for us, because it's what we can detect, are what we call compact binary mergers. So those are the mergers of two stellar-like objects that are ultra dense. So neutron stars or black holes are the systems that we're sensitive to right now. And I work on, given the data from the instrument, given that we've detected something, and trying to actually figure out what it is we saw. So extracting the characteristics of the binary, the masses of the two objects that merged, if they're rotating, how quickly, where on the sky this merger happened, how far away, all of that interesting stuff. So I like to say I'm doing actual astronomy with the detections that LIGO makes.
And we actually were just discussing the difference between gravity waves and gravitational waves.
Yeah. So gravity waves are something that people will often use to talk about gravitational waves. But technically speaking, they are slightly different. So gravity waves are things that you can get in objects like the sun, where you have gravity is basically the restoring force that creates this oscillation. So how pressure in water waves kind of creates that restoring force for water waves. In the case of gravitationally bound objects, you can have gravity be the restoring force. And so that's what would technically be called gravity waves. And gravitational waves are very different. So they're actually stretches and squeezes of space-time itself. And so when we're talking about general relativity, we often talk about this kind of fabric sheet analogy. And you think of empty space as this rubber sheet that's stretched tightly. And if it's an empty sheet, then it's like empty space. And if you throw a ball in empty space, it goes in a straight line. And if you have some massive object on this fabric sheet, it creates a curvature that other things feel. So the Earth is rolling around in the curvature of space created by the sun. But when you move things around really quickly, we can get waves that are analogous to ripples on that sheet if you move things around quickly. And so those are the gravitational waves that we're looking for.
Okay, so yeah, and that's we were distinguishing that because I sometimes get those things confused. I know I've said that a few times. But so how long have you been with or I guess would I even say technically that you've been with LIGO? You can correct me. How long have you been a part of this?
Yeah, so there's on the collaboration side, there's actually, so there's the LIGO lab, which is really the effort that's being spearheaded by Caltech and MIT. And that's really the kind of body that's driven the development and building of the laser interferometers that we use. And then in a broader context, there's the LIGO scientific collaboration. That's what I'm a member of. And that's a global group of people that are working on contributing to the detectors, but also analyzing the data that comes out. So I've been a member of the LIGO scientific collaboration since 2008.
Okay. And so, from what I understand of LIGO is that it's been a very long process of having, this whole thing set up, and then you guys fired it on in 2015, in September of 2015. Is that correct?
Yeah, so the detectors were actually operating for a long time before that. They've been operating for a couple of decades now at this point. I think they had first light maybe in the 90s. But the plan was always to have this kind of incremental approach to building instruments, because when we told funding agencies, well, I was in elementary school at the time probably, but when people told the funding agencies, specifically the National Science Foundation, that we wanted to go about measuring changes in length over 4 kilometers that are smaller than 1/1000th the width of a nucleus of an atom, they were rightfully skeptical. And so the approach was to kind of prove this technology was capable of reaching the sensitivities that people thought. And so we started off with this kind of modest approach to building the first version of the LIGO interferometers that was not as sensitive as the ultimate design that was what we had turned on in 2015. So what we call the LIGO instruments now, after their most recent set of upgrades, is called Advanced LIGO. And that's what turned on in 2015.
And pretty quick, you guys got something.
Yeah, it was surprisingly quick. We were technically not even, so what we call the duration of time where we're taking kind of science quality data, we call an observing run. And so the first observing run hadn't even officially started yet. We were still in what we call engineering time, where we're kind of kicking the tires and making sure that the instrument's operating like expected. And it happened to be in a time where both interferometers were up and running, and the quality of the data was very good. And we detected the first gravitational waves, which were from a binary black hole merger, during that engineering time before we even officially started the observing run.
And just so everybody, and I actually had a really good question that popped up, and it is relevant because I want to talk a little bit about LIGO, or have you talk about it. Can you describe briefly what the laser interferometer, what this is? Because right now we're kind of looking at a picture. I'm kind of have you blocked by it a little bit, but we've shown this a few times on stream. So if you want to tell people how it kind of works. What's going on?
So I mean, it's got observatory in the name, but it's not like classical observatories. So we don't have a piece of glass that we're pointing at the sky and picking up light. We have kind of an analogy of a microphone that we're listening to the universe with. And the construction is we have this big L-shaped instrument. It's called an interferometer. And we take coherent laser light, we split it in half and send it down each arm of that L. So each arm is 4 kilometers long for the case of the LIGO instruments. And then we partner with a third detector called Virgo, which has 3-kilometer long arms. And the light travels down to the end of these arms. It bounces back off from suspended mirrors at the ends of the arms, and then comes back eventually to the central station. And the idea is that the light coming out of the laser is perfectly coherent. So the peaks and the troughs and all of the light waves kind of line up. And if the arm lengths change relative to one another, then it changes how the light, after it's split, goes down to the end of the arms and comes back, recombines. And so if you had the arms situated so that the light coming back out of the arms exactly cancels one another out, so you have the peaks of one arm, the peak of light in one arm coming up with the troughs of the light in the other arm, then you get zero light out of the interferometers, and that's kind of their operating point. And then as you have a gravitational wave or earthquake or cars traveling around the detector, as you have any kind of disturbance that changes the lengths of those arms, then the light coming out doesn't exactly cancel out anymore, and you get a little bit of brightness out. And so we just monitor that brightness to make incredibly precise measurements of the relative lengths of the arms.
And how incredibly precise?
So we typically call it in terms of strain. So what we measure is the kind of relative length change of the arms. And so we're measuring relative changes in the arms in 1 part in 10 to the 21. So over 4 kilometers, that's like measuring the change of the length of those 4-kilometer arms to the precision of roughly 1/1000th the width of the nucleus of an atom.
1/1000th of width of,
Yeah.
okay.
So another way to put that is it's like measuring the distance to the nearest star, Alpha Centauri, which is about 4 light years away, to the precision of the width of a human hair.
So that's insane. And I have somebody in here that actually works with lasers. He asked what kind of lasers that LIGO is operating with.
That's a good question. So they are slightly longer wavelength than visible light. The actual type of laser, I don't know off the top of my head.
Well, he followed it up saying, so it's the
I know that. That's
Oh.
it's using a ND YAG laser. It has a wavelength of 1064 nanometers.
Yes, so 1064 nanometers, absolutely, and thank you for filling in the name.
Dr. Stefan in for the win on that. Okay, so it's, and he also followed up saying, so it's the polarity shift of the light. Is it the polarity shift of the light that's measured? I'm guessing is what that question
Not the
is.
polarity, just the phase.
The phase, okay. That's actually a good question. Like this, he's got very good questions. I usually don't interject too much with that, but that was a really good one. And so how often do they have to adjust these? Do you guys have to recalibrate them? Do you guys, I mean, for movements, here on Earth?
Yeah, so there's all kinds of disturbances that create noise that's far louder than the actual gravitational waves we're looking for. And so some things are just kind of run of the mill, like pedestrian noise, people noise, basically. So cars driving on roads around the detectors contribute to our kind of overall noise floor. You see the instruments are a little bit more sensitive at night than they are at day because of that. But there's also low-level seismic noise that's always at play. If we have a sizable earthquake, almost anywhere on the Earth, it can actually be so strong on the detectors that it knocks them out of lock, and we have to wait for the ground to settle down before we can put the instrument back in lock again. We have even noise created by planes flying overhead, noise created by clouds going overhead, and that kind of noise is actually what we call Newtonian noise, and that's the actual gravitational pull of the clouds on the hanging test masses that the light bounces off from. So
wow.
There's an immense number of sources of noise that we do pick up in the instruments all the time. And so our searches and our analyses need to be robust against that. And so part of the way that we go about detecting actual gravitational waves is to take the data from multiple detectors around the globe. So we have the two LIGO instruments, one in Hanford, Washington, and one in Livingston, Louisiana. Mm-hmm. And we collaborate with a third detector that just recently came back online after upgrades called Virgo in Italy. And the idea is that a gravitational wave, a true gravitational wave, passes through the Earth pretty much unimpeded at the speed of light. And so there's a coincident window that we expect to pick up a true gravitational wave in all of the detectors around the Earth, save for some effects of the location of the source on and the orientation of the detectors. But using that demand for coincidence, we can rule out a lot of the noise sources that could otherwise fool us into thinking we've detected gravitational waves when we haven't.
And for these gravitational waves, I know when it was discovered, when the first one rolled out and we heard about it in February, they were able to you guys were able to kind of pinpoint the source, right? Was it around like Cygnus? I could be wrong, but you kind of get a general idea of where the two merger, or in this case, the black hole merger for the first detection came from.
That's right. So we could constrain where on the sky that source came from to about 600 square degrees on the sky, which is a pretty big area compared to most telescopes' field of view. So I'm actually on a collaboration that uses the dark energy camera, which is located in Chile. Mm-hmm. It tries to use this large field of view instrument in the southern hemisphere to follow up LIGO events. And so that actually has a big enough field of view that we could follow up a good fraction of that localization region. But in general, it's pretty big and hard for astronomers to be able to follow up on the sky and try to find some electromagnetic counterpart to an event that can only be constrained to 600 square degrees on the sky. So the first few binary black holes that we detected were only with the two LIGO instruments online. And the way we actually localize gravitational wave events with these instruments is to use basically timing triangulation. So taking the delay time between the arrival of the signal at the various instruments that detected it, and using that to triangulate on the sky where it came from. So if we have only two detectors, then we can basically constrain where the source was to like a big ring on the sky. having a third detector like the one in Italy helps us break that degeneracy and be able to rule out a lot of that big sky area on the ring to just maybe one or two blobs on the sky. So the first event that Virgo was involved with detecting was GW 170814, which is the most recent binary black hole detection that we announced. And the difference was there that if we had just analyzed the data with two LIGO instruments, we would constrain that to sky area of somewhere around 1100 square degrees on the sky. But having Virgo in there dropped that sky area down to 60 square degrees. So it makes a really huge difference. And that was part of what made us be able to localize on the sky the most recent event, the binary neutron star merger, GW 170817.
Yeah, so it was the one in August, the black hole merger in August, that you guys were able to get a better location. And then now so now that's pretty exciting. So from the time that you guys turned it on in again, I'm just using this just informally, from 2015, late 2015 to now, you guys there's been 5 detections.
That's right. There's been 4 binary black hole detections, clear binary black hole detections. There was one marginal detection that we call LVT 151012, where LVT stands for LIGO Virgo trigger. And then we had the one binary neutron star merger that most recently announced.
Yeah, and that's the one that definitely, out of all of these, is that the one that was probably the most significant, because of, I know there was a lot of speculation going on around, these 2 neutron stars merging, and we've got to be able to detect these. But from what I understand, that would be quite difficult due to the difference in mass and the energy that would be sent out from the merging, compared to two black holes.
That brings up a good question, Ben. How different is it to detect a black hole versus a neutron star merger?
Yeah. I was going to ask.
What are the different things you have to put into the mix in order to squeeze something like that out?
Yeah, so what really drives how the signals look in our instruments is the overall mass of the binary, and specifically what kind of frequency range that corresponds to for gravitational waves. So the way to think about how our gravitational waves progress through the detectors is that we're detecting the final stages of a binary merger. So you have these 2 compact objects that are orbiting around one another, radiating lots of energy and gravitational waves, and taking energy out of that orbit results in it shrinking and going faster and faster. And so the frequency of the gravitational waves corresponds directly to the frequency of the orbit. It's a factor of 2 off. And so as they get closer and closer together, the gravitational waves they emit start off with low frequency and long wavelengths, and they increase in frequency, increase in amplitude, until eventually merging. And so the exact frequency that they merge at is decided in part by their masses. So binary black hole systems, these massive binaries, merge at low frequencies. And so our sensitivity of our detector as a function of frequency kind of forms a bucket, where at low frequency we get lots of noise from seismic motion, and at high frequencies we get lots of noise from what we call shot noise, basically photon counting statistics in the interferometer. And so when systems all enter our band of sensitivity, they're all starting to be observable in our detector somewhere around 30 hertz. And then as they progress up to higher and higher frequencies, we get more sensitive to them. And then eventually they merge at some frequency. And so for these massive binaries, they merge at a low frequency. So we only see the last few cycles, the last few orbits of the binary before it merges. For lower mass objects, they merge at much higher frequencies. So the most recent binary neutron star merger event was in our detectors for much longer, because we saw many, many more cycles, many more orbits. So for the binary black hole systems, we saw somewhere around 10 or so cycles for most of those. The lowest mass binary black hole system, GW 151226, we saw something more like 55 cycles of the gravitational wave signal. But for the most recent event, for the binary neutron star system, we detected like 3,000 cycles. And so that spent over a minute in the detectors versus hundreds of microseconds for most of the other events, the binary black hole system.
So does that mean it's actually easier to detect neutron stars than it is to detect?
It's, I would say, so it depends on how you go about searching for them. So we have a few different kinds of searches we do in LIGO. One of them is making strong assumptions about the signal we're looking for. So we know from general relativity what the gravitational wave signature should look like from compact binaries merging, so from binary black holes and binary neutron stars. So we know exactly what the needle looks like that's buried in the haystack. And so we can use that search. That's our most sensitive search for these things. And so that is, I would say, so the sensitivity, if you want to talk about it in terms of how far away we can see, binary black hole systems we can see much further away, partly because of their large amplitudes. For low mass systems, they spend much longer in the detector, but their amplitudes are much smaller. And so we can't detect them as far away. But using this kind of needle in the haystack approach where we know the needle, we have searches that are sensitive at pulling out even the low mass, low amplitude things that are closer to the detectors out of the data. We also have kind of an eyes wide open search that looks for any kind of coherent power across the network of detectors that we have. So that kind of search is able to pick out strong amplitude signals like the binary blocks, especially 150914. But it's very insensitive to low mass objects like GW 170817.
Okay, so and just for clarification, so do these to detect these neutron stars colliding? Would they have to be? You said closer. Just
yes,
for further clarification,
they have to be much closer. So the GW 170817 was around 160 or so. It was closer than 160 million light years to Earth. And the distance to 150914 was, we usually talk about it in megaparsecs. So let me think about it for a second.
You can say megaparsec, that's fine.
In megaparsecs, that's fine. So that was around 400 or so megaparsecs. So that's like 2 gigalight years.
Okay, so yeah, so that's yeah, so the distances are very different. It seems like with black hole mergers versus neutron stars, and how come? I mean, is there any reason that this was the first time we detected neutron stars? Is there anything that we did differently? I know you kind of just expanded on that a little bit, but
yeah. So I mean, the major jump in sensitivity was going to the advanced detectors, which turned out in 2015 versus the previous versions. And after that, I mean, there's been slow improvements. There's been minor improvements to the sensitivity since they turned on. But for the most part, I think we got pretty lucky with 170817 with this binary neutron star merger. It was strange in many ways. So it was really nearby. We could have detected a binary neutron star merger much further away. And statistically speaking, we kind of expect those first detections to most likely be at kind of the horizon, at kind of the furthest distances we're able to detect the systems. So in part, we were a little lucky. And that's also kind of reflected in the electromagnetic components to it. So we haven't talked much about the electromagnetic side of that event yet, but the fact that it was detected as a gamma ray burst, but happened to be very close by is pretty surprising. So either we got lucky or there's something more fundamental we don't understand about these gamma ray bursts.
right, and that's I was actually gonna. That's a perfect lead in for that. Do you want to? If there's a way we can talk about this a little bit in layman's terms, kind of what happened there, because it's not only just a neutron star collision that we were able to detect with LIGO, but it's also something we saw in light.
Yeah, so this is what we call a multi-messenger event, and it's kind of the kickoff of hopefully a whole era in multi-messenger astronomy. And what we mean by multi-messenger is that we have more than one messenger of information to learn about some astrophysical event. So usually astronomy is done with purely light, so maybe light across the spectrum, radio waves, gamma rays, but now having not only electromagnetic signature to these events, but also the gravitational wave component gives us two completely separate probes or channels of information to pull interesting astrophysics out of these events. And so GW 170817 was incredibly exciting in that we detected this merger in gravitational waves, but we also detected it in light, and we actually detected it in basically every major category of light. So from radio waves to gamma rays, we detected this electromagnetic component to it. And I think it's fair to say it's probably the single most observed event in astronomical history. The paper that we wrote that summarized kind of all of the observations in gravitational waves and electromagnetic waves had 3,600 authors on it. So it was an incredibly studied event.
Wow.
And there's a whole bunch of information that we're still working on pulling out of that. I haven't looked what the most recent count was, but I'm sure it's probably well over 100 scientific publications or more probably generated from this data so far.
So it's safe to say you've been pretty busy.
Yeah, it's been pretty crazy.
So I have a question for you, Ben. What is it that you contribute to this effort, since there's 3,600 people? So based on my experience with you, you're probably not in the tunnels making sure that the mirrors are pointed in the right direction.
That's right. They don't trust me in touching the instrument. But what I do is I work on really characterizing the source given the detection in the data. So the first step of our search for gravitational waves is to find what we call a trigger, to pull out a time in the data where it looks like there might be a gravitational wave event across the network. And then I work on the tools that then hammer that data to death and try to extract out all the information we could possibly get on the event. So using our models for what the signal looks like, we can do characterization analyses that basically put estimates with uncertainties of what the masses of the two compact objects were, how fast they were rotating, and the orientation of their rotation with respect to the orbit, and then where on the sky it was, how far away it was, all of the different parameters that would go into describing this exact binary system. And so from that, we can start to do interesting astrophysics. We can start to learn about how these compact objects may have been formed and what kind of environments they've evolved in. And so that's where things are really starting to get exciting, because we start, as we have 5, 6, 7, tens of events, we can really start to characterize these binaries in a way that we can learn where they're being formed, which is something we've been unable to do with electromagnetic astronomy.
And I think one of the follow-up questions that a lot of people have posed to me that, again, I would leave it to an expert. These events, as you said, especially the black hole mergers, are pretty far away. Does it have an impact on Earth?
No, so we had to spend decades building instruments that were sensitive enough to pick them up in the first place. So the effects of gravitational waves are very minimal. So far, and you can do some back of the envelope calculations, and even having a binary merger that's about 1 Earth orbital radius away from us would produce a strain that's still like bordering on being detectable by the human ear in terms of vibrations. So there's an immense amount of energy in gravitational waves, but its effects, its tangible effects that we can actually measure, are very, very tiny. So another way to put into context some of the energetics here, in the first event that we detected, GW 150914, that system, as it merged, emitted about 3 solar masses of energy in that merger process of three times the mass of the sun in pure energy. And so to put that into context, the most energetic explosion that humans have ever been able to do is about the equivalent of turning a 5-pound bag of sugar into pure energy. So this was 3 times the mass of the sun, so about 1 million Earth masses worth of energy, 1 million Earth masses turned into pure energy. So it was incredibly energetic, but very, very hard to detect here on Earth.
Another way to think about that is that the sun shines for 10 billion years at its current state, but it only uses something like 10% of its mass, not even quite that, throughout its whole lifetime. So you take all the energy that the sun ever will emit, and that's about 10% of its total mass. And this is 3 solar masses of energy, all within a fraction of a second.
Yeah, and they do have sounds too. I was having everybody listen to the sounds of the black holes merging. The neutron stars, obviously, you said they do too. They have different frequencies. So you said that the neutron star merge was higher pitched.
Yes.
And
yeah. So there's a bunch of different visualizations we have of all these signals, and some audio versions. So we can take the gravitational wave signature. They happen to be, if we convert them into sound, they happen to be within range for the human ear to pick up. So we like to play the sounds of the detector, the noises of the detector, as well as the signals. And the binary black hole mergers all happen at really low frequencies, so you need a good bass response on your sound system to hear those. But the binary neutron star mergers go to much higher frequencies, so those you can hear on most speakers.
Awesome. And I'm trying to see if there's any other questions that are kind of, because people are actually very interested in this. I didn't realize that I had so many people. To what degree of certainty are you able to extrapolate the nature of the causation objects from the gravitational waves? That was
the nature of the causation objects?
That's the way that it was phrased. To what degree of certainty are you able to extrapolate the nature of the causation objects from the gravitational waves?
So like the objects that are going into the merger, is that?
I'm going to say yes. Let's say yes. Let's find a way that you can maybe answer that question.
Okay. Yeah. So basically what we learn the most about are the two objects that go into the merger in the first place. So there's some information that we can kind of extract on the remnant object, the kind of final object that's formed from the merger process, but it's really hard to actually extract much detail from that. So the way that gravitational waves are created in the first place is from the asymmetric motion of mass. And so that's why binary systems are such a good emitter of gravitational waves, is that you have this very asymmetric system that's rotating very quickly and creating these ripples in space-time. So once you form a final object, in the case of a binary black hole merger, a more massive black hole, it's pretty spherically symmetric. So the best thing that we can hope to see is just kind of a little bit of asymmetry left in the remnant black hole, kind of ringing down, we call it, as it settles down into a final steady state black hole. So it's actually very hard to extract information on the remnant, on the kind of object that's produced from the merger, but it's all of the details of the components that go into it that we can really learn a lot about.
Awesome. I'm just looking at a few other ones here because I kind of had my own, but so let's see. There was one here. What is the frequency range? And I guess since now you have two different ones, you can talk about the neutron and the black hole merger. You can give both if you could.
So all of them enter our detectors somewhere around 30 hertz. Exactly what frequency they come into varies from event to event to a little bit. And then they merge. So the binary black hole systems tend to merge around a few hundred hertz or so. The binary neutron star mergers merge more at like kilohertz, at a couple of kilohertz.
Okay. And Mackie did answer that, how they determine where in the sky the gravitational wave originates from. They have the Virgo facility that's able to help with that. That's been improving that significantly, from what I understand.
Yeah, I do have a question about that, Ben. What does the footprint of a two LIGO detector, like a two LIGO system detection, look like?
So it basically looks like a ring on the sky.
Does it go like, is it a circle on the sky, or is it a ring all the way around the Earth?
A ring, well, it depends on exactly where it is with respect to the two detectors that are picking it up. So if you think of there being basically a 0-second time delay between the two instruments that picked it up, then it would be a kind of a great circle on the Earth that goes over the two detectors and around the Earth. And you can come up with other like kind of extreme angles where you could probably get more of a ring in the hemisphere. But yeah, so it's, in general, I would say great circles around the Earth is the way to think of it.
Awesome. And I'm looking to see if anybody else. So someone said it's kind of like how GPS signals work.
Yeah, so it's very similar to how GPS systems work, where you take delay time kind of between a bunch of different satellites and use that to triangulate position. It's very similar. So it's also like how you can imagine how location is done with cell phone towers as well.
And Eludriel, that's actually a really good question, because I was going to ask that same one just now. Can the gravitational waves also be used to determine the outcome of a merger, like how heavy the resulting object is, and thus how much mass was ejected from the new object as either energy or mass?
No, so it's actually very hard to get that kind of information out of the gravitational waves. So we can see, if we're really lucky and we have another really strong signal, even higher in amplitude than 150914, maybe we can see some of the effects of the oscillation of the event horizon, that kind of ring down that I mentioned before. But in general, we have to rely on simulations, so what we call numerical relativity simulations, that are basically solving Einstein's field equations numerically, and kind of evolve a simulated binary system all the way to the point of merging, creating a black hole, to figure out what final masses we expect for the remnant. And so that's where those kinds of simulations are where we get the ability to estimate the amount of energy that was emitted in gravitational waves, that 3 solar masses that we were talking about for GW 150914. As far as ejected mass, so that's only relevant for when we have matter involved, that there's actually mass to eject. For the binary neutron star system, we can start to put some constraints on how much mass was ejected from the system from the electromagnetic counterpart. But that's still very difficult to do.
And is there any other objects that LIGO could be potentially used for other than just, let's say, black holes or neutron star collisions?
So the one combo that we haven't detected yet are neutron star black hole mergers, and that's something we hope to eventually detect. But we don't know. We have very imprecise predictions for the rates of those, so it's really hard to say exactly when we would expect to start detecting them. Other kinds of things that can emit gravitational waves are pulsars, so rotating neutron stars. If they happen to have some strong asymmetry, then they would create what we call a continuous wave source. They would be a continuous wave source, and they would make basically a sinusoidal gravitational wave that we would pick up, and we have to basically accumulate lots and lots of data and integrate it to pull out those really quiet signals that might be there. So there's the potential for these continuous sources, these rotating neutron stars. There's also the possibility of supernovae. So if a supernova explosion is exactly spherically symmetric, then it wouldn't create any gravitational waves at all. But if there's some asymmetry in the supernova explosion, then we would expect it to generate some gravitational waves. Most simulations predict pretty small amplitudes for those gravitational waves, though, so it would have to be very, very close by. It would have to be a very nearby supernova to get lucky enough to detect it in gravitational waves. The only other source that we typically talk about, there's a few others, I guess. There's a stochastic background, so kind of like a general low-level hum of gravitational waves that may exist in the universe. And so that's something that would, for example, be produced by a binary black hole population. Eventually, we may get sensitive enough to pick up kind of the overall hum of gravitational waves from all these binary black hole mergers going on in the universe. And then there's also some more exotic things like cosmic strings and things that could potentially be gravitational wave sources, but those are pretty speculative.
And this is something that I've actually heard from a lot of people too, and I think it's actually not a bad question at all when people ask. I have no idea. Since this is an Earth-based observatory, is there any plans, do you think, that they're trying to move something like this into space?
Yes. So the project that is the closest to launch is called LISA.
Mm-hmm.
And that is a space-based interferometer that was originally a joint mission between NASA and ESA. And over the years, it was kind of delayed, and then eventually NASA had to prioritize other missions. So then it became largely an ESA-based mission called ELISA. But we had recently a launch called LISA Pathfinder, and the approach here is that for new technology going into space, we need these kind of Pathfinder missions to demonstrate basic functionality of some of the new hardware that's being flight tested for the first time. And so the LISA Pathfinder mission launched, and it was a great success that demonstrated a lot of the key engineering aspects that are necessary to do this measurement in space. And so LISA is still moving forward, and I think NASA is trying to reprioritize and is hoping to reinvest in the LISA project. And hopefully it will fly in the not too distant future. I think the projected launch date is somewhere in maybe late 1920s, early 1930s at this point. But there's absolutely plans to go to space to do gravitational wave astronomy, and it will open up a completely different window to gravitational waves. So far we've been seeing kind of the gamma rays of the gravitational wave spectrum. We've been seeing the very high frequency stuff. When we go to space, then we get sensitivity at much lower frequencies. And so, like I said before, the higher mass binary you go, the lower the frequency gets. And so space-based missions like LISA will give us a way to see supermassive black hole mergers, so the mergers of these black holes at the centers of galaxies, which is an incredibly exciting unprobed part of the parameter space that we are looking forward to opening up eventually, hopefully within our lifetimes.
Yeah, and I mean, this whole thing was kind of crazy because at least from, someone who's pretty passionate about all things space, this became so much a common thing. Like I thought this was going to be super novel, that we would find these black hole mergers and then we'd have a detection. We'd have to wait like another, maybe 20 so years. Is this what you guys thought? Did you guys think that, you talk about predictions that you guys have, and obviously from a much more educated standpoint, is this what you guys thought? Or did it blow your guys' mind?
It depends on the type of source. So binary neutron star mergers were always, we kind of thought of them as our bread and butter source. There were things, we knew binary neutron star systems existed, and that there should be enough of them merging that we would be lucky enough to see them with the LIGO project. we didn't know the rates well enough to really have a good idea of when we would be sensitive enough to detect them. I think we were all pretty mentally prepared to not having the first detections until something like 2019, 2020, when we started to get closer to our ultimate design sensitivity. The thing that we had a much poorer understanding of theoretically before detecting were binary black hole mergers. So those are systems where there's really no actual matter involved. It's just two vacuum black hole objects. And so they don't emit any electromagnetic light that we can think of. And so there was no way we could really learn about them before LIGO turned on. And so there was something that was very uncertain, but I think we were all a little surprised at how frequently it turns out the universe likes to merge binary black hole systems. And
Right.
so right now we're detecting the sensitivity of the instruments. We're detecting one binary black hole merger a month, more or less. Yeah. And so our instruments are down for more upgrades right now, and they'll be turning on in about a year. And when they turn back on, we expect to have a sensitivity that will give us about one binary black hole detection per week. And then as they get towards design sensitivity in kind of 2019 or so, then we'll be having about one binary black hole detection per day.
Wow.
So our garden hose is really quickly turning into a fire hose. And,
yeah.
It's going to be a lot of science.
Speaking of that, how much computer time does it take to analyze a single system? And are you going to be computationally limited as you go forward?
Yeah, so right now it's not even so much the computer resources that limit us as much as it is the people power. So we're close, but we don't quite have a fully automated analysis chain for following these events up. And so the parameter estimation, the characterization stuff that I work on, depending on the source, so for binary black hole systems could be done in basically a couple of hours. For binary neutron star systems, because they're so long, they take much, much longer to run, and those can take weeks to run. And so what we really need to do are work on the automated aspects of the following up. So not having to have people in the loop the whole way and really hand-holding all of these analyses. That's where I think we're going to hit a bottleneck really quickly with higher event rates. But there's not a fundamental barrier to that. And it's just a matter of getting the development in during this year of downtime that we have now to get ready for the onslaught of gravitational waves that are going to be coming soon.
And are they going to be opening up new observatories across the globe? I know that we have now, Virgo. Are there other ones in the works of being built or being proposed to be built?
Yeah, so there's a project in Japan called Kagra, which is a underground observatory being built that is shorter in arm length compared to LIGO, but it's cryogenically cooled. So basically trying to use cryogenic cooling to balance off the sensitivities of the loss of sensitivity that they have by using smaller arms. But that's hopefully going to be coming online in the next few years. And there's also a project called LIGO India, which is to take, we used to have in the Hanford Observatory of LIGO, we used to have two co-located detectors, one with the 4-kilometer arms that's still there, and another with 2-kilometer long arms. And during the advanced LIGO upgrades, we took the second shorter armed interferometer out of Hanford, and the plan is to build a facility in India to house that, to be a full 4-kilometer long advanced LIGO detector. And so that'll be a few years after the projected finish date for the Kagra Japan mission. So those are the two that are probably the most closest to completion.
Here's a question. In looking at the paper where they did the neutron star merger, I couldn't see a signal in the Virgo data. What was it? Very subtle, and how did it contribute?
Yeah, so the sensitivity of Virgo is still much less than the LIGO instruments, and that's for a few reasons. One of them is that they were having a hard time with the suspensions for the mirrors. So the way that LIGO operates is it has fused silica fibers, basically glass, like incredibly thin glass rods that suspend the 40-kilogram test masses. And Advanced Virgo was trying to do something similar, but was having problems with those suspensions breaking. And so they had to make a last-minute swap out to kind of steel wire suspensions, and that hurt their sensitivity by quite a bit. But there's a lot of other noise sources that are still being tracked down in Virgo. And so they're not as sensitive as the LIGO instruments. And for this particular event, it happened to be that the gravitational wave source was in one of the poor areas of visibility for Virgo. So these instruments have kind of, you think of it like an antenna pattern, and it's kind of a peanut shape centered on the on the detectors. So they're most sensitive above and below the plane of the detector, and they're least sensitive in the plane of the detector. And so it happened to be that GW 170817 was in one of those dead spots of the detector where it was having a particularly hard time pulling out the signal from the noise. And so it's more of the fact that we don't see a strong signal in Virgo that helps us in narrowing down the sky location. So for most of if you think of just the kind of ring-like localization from the two LIGO detectors, a lot of those places on the sky that the two LIGO detectors can constrain the signal to would have had a strong signal show up in Virgo. And so by having no clear strong signal in Virgo, we can rule out a lot of that area on the sky that the two LIGO detectors alone can constrain the signal to.
So Virgo kind of put in an exclusion region rather than an inclusion region.
Yeah, I would say that was really the dominant effect of the Virgo data for this event. For GW 170814, the most recent binary black hole merger, it was the case that there was a stronger signal in the Virgo data.
And so people are actually asking, like, but I think a good question is does the length of the arms matter? I mean, as far as like you have one that's got smaller arms than others. So, I mean, what does this do?
Yeah, so the length of the arms, longer arms make a more sensitive detector to a point. So really what matters is kind of the duration that light spends in the detectors compared to roughly the period of the gravitational wave that we're trying to detect. So in practice, what we would really like is something like 40-kilometer long arms for our detectors. And what we do to get close to that is we set up what's called Fabry-Perot cavities in the arms of the detectors, where light, there's actually a return mirror on the inside of so if we have our L-shaped detector here, we have our end mirrors, but we also have mirrors close to the central station that bounce the light back out to the end stations again. And light bounces back and forth, I think, roughly 150 times or so in the arms to simulate a much longer arm length to the instrument. And so that bouncing adds noise compared to if we had just had a much longer arm in the first place. And so that's really the trade-off in terms of sensitivity, is how much you have to bounce that light back and forth to have the optimal amount of time for light spending in the chamber. And so having longer arms means less bouncing back and forth.
Gotcha. And someone actually had a really good question, because as we know, the finding these were really, really cool, finding the mergers, because of general relativity. Einstein ended up being right again. And I always like to tell people that we wouldn't even have lasers without Einstein. But someone said, other than helping confirm GR, does LIGO teach us more about the nature of space-time? That's a really good question.
So I mean, we're testing general relativity in a few ways. So the fact that these gravitational waves are produced and are detectable in the first place is kind of a validation of general relativity. Exactly what these signals look like, the morphology of them, is all as predicted by general relativity. Another test that we're doing is the speed of gravitational waves. And GR predicts that they would travel at the speed of light. And so far, especially with the most recent event with GW 170817, having light and gravitational waves that we can look at the difference in the time of arrival is still totally consistent with gravitational waves traveling at the speed of light. But as far as, so that's kind of testing fundamental physics. Where we can start doing other interesting measurements is in learning about compact object formation. So by learning about these masses and spins of these compact objects, we get to learn more about how they're formed. And in terms of more fundamental physics, the binary neutron stars give us a really special laboratory for looking at kind of particle type physics. So neutron stars are incredibly dense. They're basically a star worth of mass in terms of an atomic nucleus. So it's packing together a whole bunch of these atomic components really, really tightly. And these neutron stars have much, much higher densities than we could ever hope to produce in a lab. And so by looking at the light emitted and the gravitational waves produced by these mergers, we can really probe physics at a completely new level that isn't possible in a lab on Earth.
And someone did ask way earlier, but I wanted to save that because we are kind of going to wrap up here. You've been very generous with your time, so I appreciate it very, very much. I know you're slammed. I know it. But with how is LIGO actually funded?
So we're largely funded by the National Science Foundation. So taxpayer dollars is how we're funded.
NSF, guys. So that's so cool. And I'm just going to ask real quick, just for everybody in the chat, if you guys have any questions I don't want to take up too much of his time. So I'm going to give like another maybe like 3 minutes for questions if you guys have them.
Happy. But let me just make the point though that this is a mission that could not be funded now. So the National Science Foundation really went out on a limb and invested in a very risky project that ultimately paid off. But with the way that funding is really tight in science now, and the way that these types of things have to be prioritized, a mission like LIGO could never be funded in the current funding environment. So it's a kind of a shame that this is the last kind of moonshot of its kind, at least for the foreseeable future.
We have, and that's good to note too. Is there any particular reason for these gravitational waves to travel at light speed? Since I believe that someone said, this is someone from the chat, since I believe the actual since I believe it's the actual fabric of space moving, it would not be constrained by light speed as particles are, or are they?
Yeah, so if you go to the equations in general relativity and you do the kind of approximations that are these kind of small perturbative things that generate waves, then you get out that these things should be traveling at the speed of light from general relativity. And thinking about it in more of a particle wave duality kind of thing, if we think of gravitons as being the particle carrier of gravitational waves, then that's to say that gravitons are basically massless, and they should, if anything, massless should travel at the speed of light.
Gotcha. And yes, Volke says something very important. I guess we need to ponder how to prioritize science funding moving forward. Good to consider. It is. It absolutely is. And we have one saying, what's the percent of light lost in the Fabry-Perot system? I might be botching that name. I might be botching that name. Sorry.
Yeah, I can't answer that one. I'm sorry. That's beyond my knowledge of the instrument.
It's beyond my pronunciation skills.
Well, you said that it's about 150 watts inside the system. I thought it was closer to a kilowatt, but
no, 150 bounces back and forth of light.
Right, but usually the lasers that they input into it are about 1 watt lasers.
Yes.
So the way it would work is that you send in laser light, and then the mirrors themselves are only like 99% reflective, and so you get 100 bounces. So if you send in 1 watt of laser light and you have a 99% reflective mirror, you'll get 99 bounces of that light.
Yeah.
And so that takes you from 1 watt going in to 100 watts inside the arms. So that's kind of that's a typical scale for who was it that asked the question? Junio.
Yeah. That was a good question. Let's see. So someone said, and actually, Taco Cat, I agree. What is the goal? Well, not I agree, but it sounds like a very basic question, but sometimes the most basic questions are the best questions. What is the end goal for detecting gravitational waves? What's the end goal?
The end goal is to really learn about the universe in a new, unparalleled way. And so, beyond the kind of interesting engineering feats that needed to be done to make an instrument this sensitive, as far as astronomy goes, it's really kind of satisfying our curiosity of how the universe works and how these astronomical objects are formed, how they evolve, and being able to probe this universe in a completely new way. So it's really, the most important thing is the kind of satisfaction of human curiosity and trying to learn more about the universe that we're in.
Absolutely. And then someone says, will the retooling upgrades increase range or just the level of detail in the data? What new discoveries so you hope for with the new volume of detections? Are there any new discoveries, if there are any?
That's so our improvements to the detector are in part to just lower the noise floor across all frequencies. And so that is, you can think of that as increasing our range so we can see further away. But in order to increase our range, in order to see further away, that means we also see nearby objects with better detail. And so it's a little bit of both. It's improving our overall sensitivity, but also broadening the band of sensitivity that we're sensitive to. So pushing to lower frequencies through the seismic barrier. So getting down to 20 hertz or maybe 10 hertz, where we can start seeing systems at 10 hertz would be really exciting. And then on the high frequency end, being able to see things with more detail at kilohertz. And that will be able to open up a new range of discoveries as far as the behavior of matter with these binary neutron star mergers, and we can start to probe the exact composition of or how the density varies in these neutron stars, what we call the equation of state.
And that's pretty. So wait, would you have power reduction? And I'm only going to answer if there's two more. If there is two more, this is I think might be the last one. Would you have a power reduction? Wait, I think that I don't know if I'm reading that right. Power reduction, right? There is no amplification once it leaves, right? So would you? It would be. You would be approximately 900. I don't even know how. I can't even. Those are. That is very technical laser speak. Sorry, I'm not good. Do you want to try
that question?
Okay,
after,
thank you.
After we're done.
Thank you. How about you take that one? So LIGO can see things that other forms of wait. So LIGO can see things that other forms of astronomical observation cannot.
That's right. So binary black holes are something that we have never, and we probably never will see in electromagnetic light. They're these vacuum objects that have no matter and emit no light, kind of by definition. So we don't expect there to be any electromagnetic counterparts that could ever be detected from binary black hole mergers, and that leaves gravitational waves as being the only way to really observe these systems.
Awesome. Well, I think at this point, I don't want to take up too much. We've got 7 o'clock on the dot. Got to respect the time, and I know you're busy. So wanted to thank you again. And I know that everybody, my chat was super active. And I got to say that this is like the most active they've been in asking questions. And that is amazing. So I think people might be slightly interested in this topic.
Yeah, well, it's really exciting. It's exciting to have so much excitement around this. I mean, we've all been working on this project for quite a long time. And until 2016, when we announced the first event.
Yeah, it's been boring for decades.
Yeah.
Boring for decades.
Yeah, but
yeah, so I'm really happy to be here, and thank you for inviting me.
Of course, yeah, no, and this is a very amazing community. So I'm actually pretty shocked. I've never seen these many questions and to the scale. So good job, Skynet. You guys did a great job, and then also thank you, Dr. Ben Farr. Thank you so much, and guys, I have linked to all of his stuff too, yep, that's it. So thank you so much. Appreciate it.
Great.
Keep
Thank
the
you.
great
Thanks
work.
a lot, Ben.
Thanks.
All right. Bye, guys. That was amazing. You guys are so awesome. I have nothing but you guys make me so proud. What a nice guy. No, it was you guys. That was all you guys.